that's what you get if you multiply through everywhere that you see temperature. You multiply through all the terms and then separate them in order to get all the terms with temperature on the left-hand side. So of course I can just do the division, and so you get temperature equal to the initial temperature times these heat capacity values Okay, so let's see what information we're given about all that mess. All these moles that you see me writing up here are just moles of nitrogen. So we're still using nitrogen as the basis, so I'm just saving myself a little bit of time. And so you get, if you do math, so all we need to know are these heat capacity terms, the delta H of reaction, and already you can tell me what the temperature is as a function of conversion for an adiabatic reaction. So let's put some numbers in just to give you guys some ideas of what this looks like in reality. So if conversion is 0, what's the exit temperature of the reactor? T0, which is 373 Kelvin. Right? If I don't do any reaction, nothing happens. At 25% conversion, you're up at 597. At 50% conversion, you're all the way up at 870 Kelvin. And at complete conversion, you're up at over 1600. Okay, so we'll ask an easy question first. If I want to run this isothermally, do I need to remove heat or add it? Right. So I need some sort of stream that I can heat up that I'm going to put in contact with this. So if I'm dealing with a PFR, I might have a shell around my pipe, right? And that core shell heat exchanger will remove heat. If I'm dealing with CSTR, you build a jacket, okay? So, a harder question. Yeah.
So you have to remove heat because it's an exothermic reaction, right?
Yeah,
okay.
right. And that's why as the conversion happens, the temperature goes up. So maybe a harder question. Will this actually happen? Like if I started a reactor and I let it go, you know, I had a huge amount of catalyst, right? And I'm not adding heat or removing heat, and I just let the reaction take off. Will I get to 1650 Kelvin? Why?
Because it's an reactor to get 100% conversion, and because you'll lose some heat to the ambient.
So say the first part again.
It takes the infinite reactor gets 100% conversion. And because you'll lose some heat to the ambient.
Okay, that's true, but would I get to 100% conversion?
Equilibrium?
Yeah. So never forget, I don't think you will after the test. All reactions are reversible.
So as products increase.
So of course I wrote it as an irreversible reaction because under certain conditions you can treat it as an irreversible reaction. That just means that the reverse rate is negligible. But I could have still written this as a reversible reaction. It actually wouldn't have changed anything that we did over here at all. You notice that we didn't put the rate of consumption of nitrogen or hydrogen or rate of production of ammonia in this equation at all. We will later, of course, once we come back to reactor design equations. But you know, what you're actually going to do is hit some equilibrated conversion, which depends on the temperature, depends on the pressures, so it's hard to guess what that would be. But no, you wouldn't actually hit this. And of course, you could have many other issues, like you're going to be losing heat to the air, but you know, you also could be melting your reactor, right? So there's a lot of issues with this type of thing, and that's why in most systems we don't really want temperature to change in a reactor within an industrial unit. We would much rather pick a temperature where we want to operate at, and then what do we have to do is we have to essentially turn our reactor into a heat exchanger so that we can remove that heat. Yeah.
That's what I was going to ask. Is it like kind of redundant to say you go back, you set Q not equal to 0, find Q, and then design it around Q as just like.
That's not a bad way of thinking about it, but remember that. Yeah, you'll be given Q as a function of convergence. So that would work pretty well for a CSTR. It doesn't work as well for a PFR, and we'll see reasons for that later. But no, adiabatic systems are not actually common in industry. They're common in your general chemistry or P-Chem lab, if you guys take one of those, where you're doing a reaction in a beaker, right? You're not usually setting up some heat exchanger to work with that. That's not saying you never are. But no, this is not how we want to do things. But you see that the amount of heat can be tremendous, right? You can have huge amounts of heat released from the reaction. And that's part of the reason why we can neglect things like shaft work. Because the amount of heat released from reactions or consumed by reactions is usually a very large number compared to something like shaft work. Right, so let me make sure we have all of our bases covered before we move on to the next lecture notes. Yeah, we're good. So we'll keep reusing these concepts, but that's essentially chapter 11 in the 5th edition. He doesn't do a lot there except sort of set up the concepts of how do we do these energy balances, how do we solve for heats of reaction, the heat capacity terms. We're going to start now in chapter 12, which is now we're actually going to have reactors that we can exchange heat with, so non-adiabatic reactors.
Quick question.
Yeah.
So I'm guessing like for this in design of these reactors, it's safety purposes to make sure the temperature stays below the flash point of certain chemicals that you're creating. So like you would have design parameters around that. Is that how that works? Like you need to maintain it under a certain temperature as it's reacting?
Yeah, I mean, it depends on the conditions. So flash point is in air, right? You
Yeah.
have to have oxygen for something to spontaneously combust. So there's many reactions that operate above flash points for, like methane, for example. You just have to avoid the combustible mixture, so you can't flow oxygen into the system. If you have too much oxygen, you blow, right? And in fact, people study, even in chemical engineering, people study reacting methane with oxygen in order to make my unbalanced chemical reaction up there. And so they actually have to worry about this. They have to make sure that the mixture of species that they're flowing here is never combustible. 'Cause, I mean, they'll be doing this at 700 Celsius, so it's certainly hot enough to blow. So they actually have to worry about this a great deal, and there was a recent, not a big safety incident, but there was one, where they were having an issue with one of their regulators. So the person shut off the methane cylinder, and they run methane rich, meaning that they'll be at like 99.5% methane, 0.5% O2. And that's not within the flammability limit. But they shut off the cylinder, so this partial pressure, this mole fraction starts to drop, and the reactor, it's a big tube reactor like you guys have heard about, and it's sticking, you know, it's inside of a furnace, and the end of it just turns into a blowtorch. So it is things that you have to worry about, but yeah, that's really only when you have oxygen around. A lot of reactions where you do have to worry about that, you're not, you know.
Well, I mean, it's just realistic that there's sometimes oxygen always there, right? But, you know, you can't.
It depends on the reaction. There's certainly reactors where you operate them where there might be a leak,
Yeah.
but as long as you're beneath the flammability limit, you're not going to be hurt by it. No, so like in my lab, for example, we have a big tube furnace, and so we have hydrogen, oxygen, so we actually have 4 lines for this unit. This one is helium, oxygen, and this is 1% oxygen and I think nitrogen.